Okay, so what if the bearing is subjected to the variable loading? So previously we were discussing this bearing subjected to the static loading, right? So, but if this bearing is subjected to the variable loading, how to evaluate its life? Okay, so this is the point that we are going to discuss in this lesson. Okay, so we can define if this bearing is under the variable loading. Okay, so we define the F. We can obtain this figure by experiment. This figure is correlated with the force versus the life. Okay, therefore we can plot the figure of the F, the force, the power of A, okay, which depends on what type of the bearing you are using, okay, and the life. Okay, so we can get this experimental uh, plot, right? Okay, and then we define the linear damage. It can be defined as the linear damage hypothesis. That is in the case of the load F1, the area under the curve from the L equals to 0 to L equals to LA is a measure of the damage, D. Okay, therefore define the damage, engineerily defined, the damage equals to F1 per of A times LA. Therefore, we define the F part of A, L equals to constant. Okay, so from this plot, we can observe that the area under, under this curve with the F1 part of A times L1 is the area. Okay, therefore define this area is the damage. It's the damage. Okay, so for this case, it's F1 part of A right here, and the life LA right here. Therefore, the damage is defined as the area under this curve. Okay. Okay, so if this bearing is subjected to the variable loading with piecewise constant loading. Okay, so if this bearing is under the variable loading with the F and the life L1, the lowercase L1. Okay, so what type of the piecewise loading or what type of the periodic loading of this bearing is? So for the first cycle of this damage, we say the FE1 part of A times L1, right? And for the second damage, it's defined as the FE2 part of A times L2, and so on, right? And so on, right? And then we define the FEQ is the equilibrium static load inflicting the same damage when run for L1 plus L2 plus L3 revolutions and doing the same damage D per period. Okay, so if this bearing is under the piecewise constant loading, we'll define a load FEQ, which is an equilibrium static loading, corresponding to FE1, FE2, and FE3, and so on. Okay, so we engineerily defined it. The damage of this periodic loading, D, right, is the FE1 part of A times L1, and FE2 part of A times L2, right? Blah, 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 and so on. Okay, and we define there is an equilibrium force, equilibrium load, FEQ, part of A times L1 plus L2 plus L3. and these two damage equals to each other. Okay. Okay, so therefore we can rewrite this, right? So these two are equal with each other, right? Okay, so we can manipulate, put this D here, right? This D here, right? And this, we just rearrange this equation, we get the FEQ equals to this term, right? It's quite easy to understand, right? So we can just rewrite this term in this formation. Okay. So here the Fi is the fraction run up under load FEI, which is not equal to the FEQ, is FEI, right? And the Li, okay, can be expressed as the Ni times Ti. Okay, here the Ni represents the rotation speed at FEI, and the Ti is the duration time. Okay, it's the duration time. Okay. Oops, sorry. Okay, so we can rearrange this equation. Let me clean up those. We can rearrange this equation, right, to get the FEQ after replace by the FEI, Fi, and Ni times Ti. Okay, so we get equilibrium load equals to this term. Okay. Oops. Okay. Okay, so for here, we need to apply the safety vector. Okay, so this is the FEQ, right? Equilibrium load. And we need to apply application vector, or we say it's a safety vector. Okay, so this force here, FEI per this FEI, this force has to be replaced with a safety vector times the FEI. Okay, here, so we get this equilibrium, the FEI for the practical scenario. You have to apply the safety vector depends on different applications, right? Okay, so this AFI represents the application factor, or we say the safety vector. Okay, and then we define the equilibrium life equals to K over the FEQ part of A. So the FEQ is equilibrium load, LEQ as the equilibrium life. Okay, equilibrium life. Okay, so there's one examples here. So we can just so understand what those calculation is by this example. So a ball bearing is run at 4 piecewise. Okay, so it's a piecewise loading, continuous static loading, as shown in the following table. Okay, this table. Okay, so column 1 and 2 and 1, 2, and 5 to 8 are given. Okay, given in this table. Okay, and the column 1 and 2 are multiplied to obtain column 3, right? 1 times 2, you get the column 3, right? And the column 3, the entries divided by the sum of the column 3, 2600 to get column 4, right? 3 divided by 2600, got it, the column 4. And column 5, 6, and 7 are a radial axial and the equilibrium load, okay, respectively. And column 8 is the appropriate application vector. And column 9 is the product of the column 7 and the column 8. Okay, so for the column 3, it's a product, right? It's a product of the column 1 and 2. So the column 1 is the time fraction, and column 2 is the speed, RPM, right? It's time RPM. Okay. And the column 4 is the column 3 divided by 2600, right? So it's a summation of the column 3. Okay, column 3. Okay, so from this equation, we get A equal to 3, right? So it's the ball bearing, and the equilibrium radial load is Fe is the, okay, so we get from the equation, maybe I'm not, or here. Okay, from here, okay. Okay, so we got this equation, right? So it's the 884 pound. Okay, without apply the application vector. Okay, so the Fi for here is the 0.077. Okay. Okay, here. Okay. And for this 0.115 here, and 0.346 here. Okay, and so on. Okay, so and then we get a equilibrium load. Okay, equilibrium load. Okay, so for the next case, the variable loading with the piecewise constant load. So after several levels of loading, how much life is left if the next level of the stress is held till failure? And failure occurs under the linear damage hypothesis when D, the damage, equals to constant K equal to F power of A times L. Okay, so as I mentioned previously, this the equilibrium load power of A times the equilibrium life equals to this term, right? Okay, equals to this term. And we define the D is a constant K here, right? Okay, from the previous the linear damage hypothesis, the constant or say the damage equals to, right? Fei power of A times Li when this damage occurs equals Fe2 power of A times L2 and so on, right? And then the K damage equals to Fei power of A times the lowercase 1. That's mean for the first piecewise loading with its life revolution. Okay, revolutions. Okay, okay, and the same for the second load, the piecewise load times the second life. Okay, and the third load times the third life. Right, and then we can plug this K here. Right, so in for this case, this FEL just rearrange this L to the left as the denominator here. Okay, so we got the K over L1. Similarly, we got the K over L2 in capital L. And therefore, 3 power of A equals to K over L3. Right? So we can just extract the K outside, and we get the K damage times the summation of the lowercase li over the life L, a capital Li. Okay, and then we have to obey this equation, right? K equals to K times the summation, right? Therefore, this term has to be 1. Okay, this term has to be 1. Okay, so the second case of the variable loading, that is the periodic variation. So for the previous case, we have this piecewise static loading, right? So we have this static loading like this, right? However, in this case, which is not static, it's not static, it's variation. Okay, it's a variation. Okay, it's a variation loading. Okay, so a cam whose bearings rotate with the cam through the angle d theta, and the total damage during a complete cam rotation. Okay, the damage equals to the integration of the damage from the 0 to phi, right? 0 to phi, f power of a times d theta, okay, d theta, okay, equals to the FEQ power of a times phi, okay? Therefore, we can just rearrange, right, this equation to figure out what is the equilibrium force with the periodic variation, or the variation continuous loading is, right? So this equilibrium load will equals to 1 over phi integration 0 to phi f power of a d theta, and part of the 1 over 8, right? And the phi here equals to 2 pi. So the integration is from the 0 to 2 pi. Okay, from 0 to 2 pi. So this can rotate a circle, right? Rotating one circle. It's 2 pi. Okay, it's 2 pi. Okay, a static equilibrium load does the same damage as a continuous varicyclic loading. Okay, that's the definition. That's the definition of this. We define this periodic loading, get the same damage as the variation loading. Okay, piecewise variation loading. Okay, so this is one example. I just skip it. Okay, just skip it. Okay, so next we're gonna focus on the tape roller bearing. So if you still remember what we learned previously, the ball bearing and the roller bearing, the ball bearing, which can be subjected to majorly the radial force or the radial load, and with the small axial loading, right? Axial load. Okay. But for this taper roller bearing, okay, can be subjected to the high radial and the axial loads. Okay, so for this bearing, which is the straight roller bearings, can carry large, okay, large radial load, okay, but no axial load. This is one first case, can carry the large radial load. and without any actual load. Okay, for this straight roller, sorry, which is the straight roller bearing, okay, which is not the taper roller bearing. Okay, so for the straight roller bearing can carry the large radial load, but no actual load. Okay, and for the ball bearings can carry the moderate radial load and a small actual load. Okay, and for the taper roller, this is the case that we are going to discuss today. Okay, this taper roller bearing rely on roller tippet at an angle to allow them to carry a large radial and the large action load. Okay, and taper roller bearings were popularized by the Timken company. Okay, so well, you can just refer to this website of this company. So this company defined the spec of those taper roller bearings. Okay. Okay, so this is the scheme of the taper roller bearing. Okay, so this is the taper roller bearing. Okay, so there's the outer face resultance force, which can be separated into radial and thrust, or the actual loading. Okay, and usually this taper roller is be as though trace of the optical elliptical roller rib contact. Okay. Okay, so this is the case. Okay, the floating cylindrical roller bearing left here. This is the straight, right? Straight roller bearing, right? It's a straight roller bearing, okay, which can only carry the radial force, but no actual load. And for the left, is fixed two row taper roller bearing. So we have two, one, and two. 1 and 2. Okay, it's becoming the preferred method for managing loading conditions, seems in wind turbine gearboxes. Okay, so there's some terminologies, or we're gonna, and the geometries we're gonna have to realize first. Okay, so for this taper roller bearings, there are two separate parts. One is the this cone assembly. Okay, cone assembly, which includes the cone, right? And roller and cage. Cone, roller, okay, and the cage, cup, the cage, which is the such like separator, okay, like separator of the ball bearing. Okay, this is for the we say the inner. Okay, for the inner. Okay, for the inner. And for the outer, we're gonna focus on the cup here. Okay, the cup here. Okay. And rollers are tapered, so virtually apex is on the shaft central line, and taper allows for pure rolling of the angle rollers, and the distance A locates the effective actual loading for forces analysis. Okay, so what's this mean? Okay, so rollers are tapered, so virtually apex is on the shaft central line. So that means we have the force, right? This is the roller, taper roller, right? We have a force line. Okay, we have a force line, right? We just extend the force line. We get an intercept with the shaft central line. Okay, so the point here, defining a G right here. Okay, and this G with the distance A. Okay, so the distance A locates the effective actual location for the force analysis. Therefore, we define this A, this distance, is effective actual location, or the effective actual distance. So we analyze the stresses based on point G. Okay, based on the point G. Okay. Okay, so some engineering drawing for this taper roller bearing. Okay, taper roller bearing, and there are other effective means to support the bearing. Okay, when it is subjecting to the action loading or the thrust. Okay. Okay, that depends on how you design. You can use the taper roller bearing, or you can just use the other means to support the bearing. Okay, such that they can take the thrust load. Okay, is to have the shoulder. Okay, for both shaft and the housing bore. Okay, either use the taper roller bearing or you use the shoulders. Okay, so this figure just shows this assembly figure of the taper roller bearing, right? So as I mentioned, the cage is the just like the separator of the ball bearing to separate the roller and the trace. Okay, and if you don't want to use the this roller, taper roller, you can use the shoulder. Okay, so we can define a shoulder design here. We can have the shoulder design here and here, right? It's the shoulder design here. And this shoulder design is also the most effective means, okay, to against the to be against the thrust or the actual load. Okay. Either way, okay. Okay, so the mounting direction of the taper roller bearing. Okay, the mounting direction. So the mount pairs in opposite direction to counter the actual load. It can be mount in direct mount and indirect mount configuration. For the same effective spread A, E, okay, the direction mounting requires the greater geometric spreading AG, and for the same geometric spreading AG, the direct mounting provides the smaller effect spread AE. Okay, so this slide just want to tell us how to mount this taper roller bearing. There are mainly there are two types of mounting. First is called direct mount and indirect mounting. Okay, so what is the direct mounting is? What is direct mounting is? That's mean the AG is greater than AE. Okay, the AG is greater than AE. So where's the AG? So what is the A? A is what I mentioned previously, is the force line, right? The force line, the extended force line, which is has the intercept with the shaft center line, right? Shaft center line is the intercept, and we define this effective location A, right? The effective location A. So from this figure is right here. Okay. If you still remember that I mentioned previously here. Okay, right here. Okay. So we define the AG, which is extend this force, extend this force line. Okay, we extend it. Right, there's an interceptor here. Right, also there's an interceptor here with the taper roller bearing and here. So in this figure, I defined the previous I defined the point G, right? So here it's the A naught, right? So it's the G, that's what I mentioned previously. And the intercept of the taper roller bearing AC here. Okay, and similarly, AC is the intercept of the taper roller bearing. Okay, so if this mounting approach has the AG as greater than AE, we define it is the direct mounting, or it is the indirect mounting. So for the indirect mounting, we say the AE is greater than AG. Okay. Okay, so this is geometric design of the taper roller bearing. Okay, so this is the direct mounting and this is the indirect mounting. Okay, so you can tell it's different. There's a shoulder design here and there's a shoulder design here. Okay, so for this indirect mounting, the AG is greater than AE. Okay, so for this for the direct mounting, AG is greater than AE. For the indirect mounting, AG is smaller than AE. Okay, depends on the force, right? The force line here and here, right? And the force line here. Okay. Okay, so it's just some geometric definition of the roller bearing. Okay. Okay, so we can check the table from your textbook, from your handbook to select what's the roller bearing or taper roller bearing that you require. Okay, now you require. Okay. Okay, so induced thrust load. Induced thrust load. A radial load induces a thrust reaction due to roller angle. Okay, so there's the induced thrust. Okay, induced thrust, Fi. And this induced thrust comes from a radial load. Okay, comes from a radial load with the roller angle. Okay, roller angle. Okay, so this is the commonly used to evaluate the induced action load or induced thrust. Okay, okay. Of course, it depends on the different company or the Timken company or the SKF company will provide you how they evaluate the induced thrust load. Okay, induced thrust load. Okay, and the K ratio of the radial loading rating to the thrust loading rating, and K is dependent on the specific bearing and is tabulated in catalog. Therefore, it is defined by the manufacturer. Okay, it's defined by the manufacturer. Okay, so this Fi is induced from the radial load. So we have the force here, right? So this force can be separating the radial and the axial loading, right? So this radial load induces this thrust. Okay, this radial load induces this thrust. Okay, so I'm going to show you how to calculate this axial loading, okay, including the induced axial load, induced thrust, and the external axial load. So the FAE defines the E means the external axial load, and the induced axial load. Okay. Okay. So the equilibrium load, equilibrium radial load for the taper roller bearing is found in a similar as before, right? So we have the equilibrium force equals to the X and Y vector. Okay, and the V is the rotation vector. Okay, the FR is the radial load, and the FA is the axial load. Okay, and for the TINCAP, the company recommends the X equals to 0.4 and Y equals to K. What is the K? The K is right here, right? Which is tabulate in the catalog. Okay. Okay, therefore the FE, the equilibrium load, equal to 0.4 FR plus the KFA. Okay, and the FA here, FA, is the net axial load carried by the bearing, including the induced thrust load and the external axial load. Okay, and only one bearings will carry the external axial load. Usually you have two bearings. Okay, right? Left and right. However, only one bearing will carry the external axial load. So how do we know which one carry the external axial load? How to determine it? So determine which bearing carries external axial load, regardless of mounting direction or shaft direction. Virtually inspect to determine which bearing is being squeezed. Squeezed. Okay, squeezed. Label this bearing as bearing A. Okay, so let's look at this bearing combination here. So if there is an external force load applied, which bearing is being squeezed? A or B? Expect virtually. Just look. Of course, A, right? So the bearing A is the bearing being squeezed by the external axial load, right? So for this case, we have the external axial loading applied, right? And which bearing is being squeezed? A or sorry, B or A? Of course, bearing A, right? It's being squeezed. Therefore, the both cases, the bearing A is being squeezed, and the bearing A is subjecting to the external axial load. Okay. Okay, so we already know how to determine this which bearing is being squeezed, right? And for the next course, I'm gonna show you how to evaluate its net axial load. Okay, I'm gonna leave this course next time. Okay, I'm gonna leave this course next time. Okay.